Guys, in this video I'm going to show the construction method of this high voltage bipolar multiplier setup and how I built it. First we're going to start off with the ZVS driver. The ZVS driver is powered by this transformer which feeds into a bridge rectifier. I'm regulating the voltage via this variac transformer which can increase it from mains voltage down to 300 volts. The reason I'm doing this is because the secondary output of the transformer isn't feeding the maximum voltage that the ZVS driver can take. All it's doing is sending the mains voltage into this transformer which steps it down. You can see I've ground my own secondary. It then feeds into this bridge rectifier which then feeds into the ZVS driver which then feeds into this flyback transformer which is operating at a around 25 kilohertz frequency. And this is going to feed into this this bipolar voltage multiplier setup. And I should be getting around maximum input voltage I can put in is around 25 volts when I put the mains at 300 volts. So this is 10 stages and I'm getting around I think 10 kilovolts from 15 kilovolts at 25 volts input. So that's around 250 kilovolts I can get. I can increase the voltage by increasing the output voltage in the transformer, but it's a bit too hard to rewind all of it, so I'm just going to leave it as it is. I'll show you some test runs with the ZVS driver running, and then I'll feed it into this bipolar setup and show you the results. As you can see, I've got a voltage reading on the variac, and to power on the ZVS driver, I use a switch. So I just need to put this up to mains voltage. As you can see, 240 volts is the mains. That humming sound you hear from the variac is because it's getting saturated. Obviously, the more I increase the voltage, the more it's going to get saturated, so the louder the sound's going to be. If I turn it on, so the ZVS driver is running. The voltage potential across this transformer is live. I'll demonstrate this without the lights so you can see it better. Alright guys, as you can see I've turned off the lights. Now you can see the voltage, the spark gap, the sparks. For a better demonstration, I'm going to increase the voltage to 300 volts in the variac to show you the how high the voltage can get in the secondary of the ZVS driver, ZVS transformer. Not just that, as you can see here, for the secondary coil, I've strung together two secondary coils from a inverter microwave, and I just put them in series to double the number of turns to increase the voltage output. I guess the downside of putting the voltage in the variac to 300 volts for this demonstration is it's going to saturate very quickly. The saturation is going to cause you're going to hear a loud humming sound across the coil, so leaving it on for a long period of time is definitely not good. Not just that, the microwave oven transformer, because there's such low turns in the secondary coil, I don't know if you know this, but I removed the magnetic shunts as well. The magnetic shunts is, in a way, it basically decouples the secondary coil by allowing more magnetic field lines to travel through the magnetic shunts to limit the current. And because I've removed that, more magnetic coupling is going to occur, which is going to increase the efficiency, of course. But this is going to increase the ability for the transformer to get saturated quicker. So the secondary coil is going to get very hot with a lot of eddy current and hysteresis losses once the transformer core saturates. And because I've welded the transformer core, I don't know if you can see here, I've welded it, the humming sound's not going to be that loud, so there's going to be more energy loss in the form of heat. And this is the downside of increasing the output voltage to 300 volts. So I can't do this for a long period of time, and it would make sense to increase the secondary turns of the microwave transformer to make it more efficient, because having in such low turns on the secondary. When the transformer is not even turned, like drawing any load, there's still going to be like 100 watts being used just to have the transformer on. There'll be like 10 amps across the secondary, which is just a massive waste of power. This is the downside of using broken materials and stuff like that. So anyway, I'll show you our 300 volts here. I'll then set up my apparatus for the voltage multiplier and measure the output voltage I can reach. Alright guys, I'm not going to turn off the light for this because I need to see what I'm doing. But as you can see here, the output voltage on the variac is 240 volts, which is basically mains. I'm going to increase to 300. You're going to hear a loud humming sound. After a short while, I will turn it off. There's a demonstration of the output voltage I can reach on the ZBS transformer. As you can see, it draws a lot of current and it's very powerful. So you can also see the wire accidentally shorted against the wire, and the reason this is possible is because of the high frequency of the transformer. So the high frequency causes something called the skin effect. This obviously isn't meant for high frequency transmission, so the skin effect is going to be present on this secondary coil, or on the wire that's connected to the secondary coil, and it actually arcs outside of the conductive material, and it actually misses a fair amount of the conductor path, so it's going to lose a lot of power. So normally you'd have I think a two wire transmission line, but I mean, it doesn't really matter in my scenario because I'm not actually trying to achieve maximum efficiency, but it does pose a danger, especially if I touch the wire while it's live. I can definitely get electrocuted. Not just that, if I touch this while it's live, I could potentially get killed because of the high voltage it's generating and the current. I think the safety about this is that since it's at a high frequency, it doesn't travel into deep tissue apparently, so I'll probably get burnt on the outer layer of my finger if I touch it across my finger. But that's still dangerous because if I burn myself at that frequency, I could definitely get carcinogenics across my hand, so that could potentially cause cancer. So this is a very dangerous system, so if you're ever going to want something like this, you just be cautious about what you're doing. And yeah, I mean, a system like this here is pretty easy to make. I mean, 90% of this stuff, I think it cost me in total, everything cost me around $60, including the bipolar voltage multiplier. But I did have a lot of resources at my disposal. I did take a lot of broken microwaves apart. I think I took down two for this. There's one transformer, and then this is the secondary transformer of two inverters actually. So that's 3 microwave transformers. And I bought the ferrite core from AliExpress. I think it's called a W/40. And then the ZBS driver I bought from AliExpress, but I originally had another ZBS driver. I'll show you guys here. The ZBS driver was made from broken microwaves, and you can see here the transistors. These transistors were used from an inverter microwave. I can show you the flyback sparks I was able to generate with this, but it stopped working. I think the transistors blew, or I think the field effect transistors. Yeah, they just got destroyed. Anyway, I'm going to connect this system up now to the high voltage setup, and we can measure the spark gap. So all I have to do is connect these terminals to these terminals, via these terminals I've soldered together. Alright, the system is on. Turn it on. Alright, that was 1.8 centimeters. I'll increase the spark gap. All I have to do is just move it back. I don't know how far this is actually. Let me get a ruler. I don't want to touch it because the capacitor's voltage across it would still be pretty high, so I'm not going to use the metal ruler. This is about 5 centimeters. Yeah, I'd say it's about 5 centimeters. So estimated that 1 centimeter is 10 kilovolts at standard laboratory conditions. I think it's fair to assume this is around 50 kilovolts. And this is at 246 volts mains. So I'll chart this down on a paper and also put this on a graph to see how far, which voltage we're getting. Alright. I'll turn off the lights so it looks better. I'll show you footage of the spark gap with lights and without lights actually. So I'm going to increase the spark gap distance now. Alright. Yeah, this should be around 7 centimeters, I believe. Oh, yeah, it's around 6. It's doing that really easily. As calculated, it should go up to 3 times more of this distance. I'm just going to move this one back here. It doesn't make sense to move this one back. Anyway, I'm going to start, see if there's a voltage across this. Alright. That's pretty far actually. See how much volt? 10 centimeters, so it's around 100 kilovolts. See if we can double this bad boy. I'm gonna put this back down here. And then I'll move. I'm afraid the transformer is going to saturate soon actually, so I'm going to turn off this system. And the primary of the transformer is getting very hot. It's not that hot, but it's getting very hot, so it's saturating obviously under no current conditions, which isn't ideal. Anyway, I'm gonna move this back. To increase the spark gap length. Then I can measure the output voltage with the spark gap distance obviously. This isn't a precise measurement because apparently past I think 100 kilovolts, the 10 centimeter law. No, is it 1 centimeter for 10 kilovolts isn't really, it's not a linear relation. Let's measure the spark gap length now. This is 13 centimeters. Okay. I don't know if it's going to make this at 240 volts, but I'll say, okay, I'm going to turn on the names. Alright, the variac's turned on. I need to flip the switch, see if we can get a voltage across it. So scared. See here, there's Corona. I'm going to increase the output voltage to 270 volts. Let's just max this out. Ooh. Alright, I'm going to turn the lights back on. This is not safe at all. Oh my god. A lot of Corona. Also just a fact, as you can see here, since there's 2 different types of transformers, one for 60 Hz mains, one for high frequency obviously. The actual core itself looks completely different. So this is iron core, this is a ferrite core. Not just that, this one has an air gap as well, as you can see here. Whereas this one is just coupled magnetically with the actual core itself. You can see it's like a piece that goes through here. Yeah, that's because of the losses that would occur if if you use the iron core for a high frequency transformer. I'm not just at the efficiency for the primary to secondary. This is so it doesn't saturate as well, obviously, because the magnetic domains inside the core actually get aligned based on the magnetic field. So once the magnetic field can't increase any domain lines, it's going to saturate. So that's what saturating is. And as I've shown you before, it saturates the excess energy. Magnetic field causes heat, which is very evident here on my finger because the spray paint got burnt off. Anyway,